Our next talk showcased the joint work between Uber and Alluxio. You might remember that there was a joint talk back in October last year on Alluxio Day event in 2021. Now, last time, Zhongting Hu and Beinan gave you a glimpse of our collaborative work in enabling Presto caching at Uber with Alluxio. Now, since then, Chen Liang from Uber and Beinan from Alluxio has dived deeper in launching Alluxio Local Cache, as well as building a customized cache filter for the performance upgrade. So today's presentation, we aim to provide the audience with some more updated work since October last year. If you are interested in reviewing the previous work, you can find the resource on the Alluxio Day page on our website, and we'll have this one ready afterwards to you. So presented to you by Chen Liang and from Uber and Beinan Wang from Alluxio. Chen is a senior software engineer at Uber's interactive analytics team and focusing on Presto. Before joining Uber, Chen was a staff software engineer at LinkedIn's big data platform, and he's also a committer and a PMC member of Apache Hadoop, and holds 2 master's degrees from Duke University and Brown University. And Beinan Wang is a software engineer from Alluxio, and he is a committer of a PrestoDB as well. Prior to Alluxio, Beinan was a tech lead at a Presto team in Twitter, and then built a large-scale distributed SQL team for Twitter's big data platform. And he has 12 years of experience of working on performance optimization, distributed caching, and volume data processing. He received his PhD in computer engineering from Syracuse University on symbolic model checking and a runtime verification of distributed systems. So let's hear from Chen and Beinan on speed up Uber's Presto with Alluxio.
Yeah, thanks, Jasmine, for the introduction. Should I share my screen? Or,
yes, go ahead.
Okay. Yeah, just try to make sure I stuck the right screen. Okay. So can you see my screen now?
Yes.
Okay. Just move everything up. Okay. Is that good? Can you see my presenting the slides? Good. Okay. So yeah, today we're going to talk about how our experience with Alluxio at Uber in speeding up our Presto use case. So basically, in the first part of the presentation, I'll be talking about some of our use cases and the challenges we face and how we address them. And in the second half, I will hand over to Beinan to talk about some work on his end. So I want to start with giving an overview of our Presto use case here at Uber. Essentially, all decision makings are data-driven. There are various use cases that involves Presto, such as pricing as in marketplace pricing, and also some legal needs use cases as in compliance, and of course data science for sure. Presto is one of the very core engines that powers all sorts of data processing here at Uber. And in terms of scale, we run in 2 regions with a total of 15 clusters with a total of about over 5,000 nodes, serving 7,000 weekly active users who run more than 500,000 queries a day and accessing 50 petabytes of data. I think the scale is pretty large, so that's where Alluxio can help us a lot. And also in terms of workload traffic pattern, basically, we have 2 traffic patterns essentially. One is the interactive pattern, where basically users run all sorts of random ad hoc queries through various dashboarding tools. The other is what we call the batch workload, but it's essentially the scheduled recurring queries. Yeah. And in terms of our Presto deployment, I think it's pretty standard. Users submit their SQL queries to a proxy layer. So this proxy layer will redirect the queries to different Presto clusters. And the Presto clusters will talk to different variants, different backend data source through connectors. And the data source I'm talking about are like Hive, HDFS, Pnode, MySQL, even Kafka. Yeah. And today, of course, the main topic would be how we use Alluxio in our environment. So just recently, we deployed Alluxio caching into our clusters, into our production. So we deploy to 3 clusters, each has more than 200 nodes. And it's plugged in as a local library, so there's no separate service, whatever. And also it leverages the Presto Workers local NVMe disks. And also we use, we're not caching all the data, but like a selective subset of data. This is what we call selective caching. I will get to that in next couple of slides. So next I'll be talking about some challenges we encountered as we got here and how we handled them. I will talk about each of them. The first challenge we encountered was what I call here the real-time partition updates. So basically the problem is that there are partitions and tables that are constantly changing. So because we use hoodie tables, which means that they support upserts into existing partitions. And the problem with that is that you cannot just use a partition ID as a caching key, because it could happen that the remote partition is already updated, but the partition in Alluxio's caching is still the before the updates. Then the users would get their old data when they run a query if the data is served from caching. So that'd be a very inconsistent experience for them. And our solution to this is actually pretty straightforward. We simply add the latest modification time to the caching key. So instead of using HDFS pass, as we did at the beginning, we use HDFS pass concatenating with modification time as the new caching key. So this time information is already available in Hive, so it's not a hard change. But this change does make sure that the users, we have the clear distinguish between the different versions of partition essentially in the cache, so there'll be no ambiguity here. So with this change, the users always get a consistent view of their data. But there's definitely a trade-off we are making here, which is that now in the cache there are basically multiple versions of the same partition all in the cache. But most likely only the most recent one is going to be helpful. So that does mean that we are using extra cache space, which could lead to a more cache eviction as well. So that's something we are still working on improving. But unless your table is changing super frequently, that's probably not a big issue. I think our environment hasn't been a big problem yet. But yeah, there's definitely room to improvement in terms of caching strategy, things like that. And our second challenge was regarding the cluster membership change. Basically, not just data could change, the cluster itself can also change. So this is basically, so if we have a node joining or leaving the cluster, that could hurt the cache efficiency of all the nodes in the cluster. That's a problem here. And the reason of that is because Presto will try to locate the same set of nodes for a given partition key. So basically for caching and for query both. So we will always keep the same set of nodes. And this is good, but the problem is that previously Presto was using a simple mod-based hash function, which can break basically when the cluster changes. Here I have an example just to be more concrete. Let's say we have this tiny Presto cluster with only 3 nodes, 0, 1, 2, and also we have one partition with key equals to 4. So with this simple mod-based hash function, for mod 3 would be 1. So the partition is located on worker number 1. And also the same for the query. Like the query also do this same function and also find worker number 1. So we're good. We found our cached partition. However, let's say a node goes down, then there are only 2 nodes. Now the hash function becomes for mod 2 equals to 0. So Presto will think that the partition is probably on worker number 0, but it's not the case. So worker number 0 can still fetch the partition and put in cache, but that's not going to be very efficient given that the partition already exists in this cluster. So our solution to this is consistent hashing. So it's actually more straightforward than you may think. So basically the core idea is that instead of, let's just not use the mod-based function. So instead, all the nodes are conceptually placed on this virtual ring, and their relative ordering is always the same. regardless of any node joining or leaving. And instead of do the mod-based lookup, we always traverse the ring to find where the node where it should belong to. So this way, we can make sure like no matter how it changes, always located on the same set of nodes. And also we use a replication here, so we not only put the partition on just that one target node, also next nodes on this ring. So this way, even if that node goes down, the next node serving this partition will still have the partition in its cache. And yeah, this solved the issue of cluster change for us. The next challenge we encountered was about the cache size restriction. It's basically that we have more data than the disk space we can use for caching. So if you recall in the first slide I put, our clusters are serving more than 50 petabytes of data daily. But like our local disk space is only like 500 gigabytes per node. So there's definitely a huge gap here. We can still, put everything into the cache and hope for the best. But like because it's mismatch, there's going to be a lot of cache eviction, and the cache hit rate will be much lower, just because we have so many data to put into the cache. So our basically the approach to this is basically to not cache everything, but we should only cache a selected subset of data. Here I'm talking about like maybe a certain tables to cache and with certain number of partitions to put into cache. So this is what we call a cache filter. It's basically a mechanism that decides whether to cache a partition, whether to cache a table and how many partitions for that table to cache based on a static JSON configuration. So basically we added this new configuration which specifies what table to cache. Here is pretty self-explanatory. Table database full and table bar and max 100 partition. And we see this helped a lot in terms of the cache hit rate. Without using cache filter, it was only like 65%-ish, and with cache filtering, we were able to make it like more than 90% pretty consistently. And there were a few notes about cache filtering. So the most notably, it is a manual static configuration, and that requires some domain knowledge. Basically, you need to be aware what you are putting into the configuration. Like ideally, this should be the most frequently accessed table, because those benefit the most from caching. And also, you need to have some sense of how many partitions that you should pick for those tables, like how many partitions are being frequently accessed for those tables. And also should put tables that do not change too frequently. Basically, this is echo the first challenge, like about the changing tables. So ideally, we want this process to be automatic and based on quantifiable numbers, like a table level matrix, which I will talk about in a minute. But we'll not get there yet. So that's definitely one of the future work item. And just to give a brief mention about our monitoring and dashboarding. So we have integrated the Alluxio metrics into our Uber's internal metric platform, and we meet the GMS metric to our Grafana dashboard. Yeah, as you can see, the cache rate is pretty high in this graph. So, and last, just to recap. So about the current status, so we have, again, we have deployed to about 600 nodes across 3 clusters. And we use cache filter to cache about, currently there are like 20 most frequently accessed table here at Uber. And we're still, we just deployed recently, so we're still monitoring and getting numbers for that. But some initial measurement has show a great improvement potential. We have seen the input scan time has been reduced to like only 1/3 compared to without cache. So that's definitely very encouraging. And the next steps, the first thing is about like the cache filter I just talked about. We want to have the more automated way and a more quantifiable way to onboard tables into cache filtering. And the Alluxio shadow cache could be the helpful tool here. And also want to have both better support for the changing tables, basically hoodie tables. And there are also other optimizations we can do, like for example, load balancing. And yeah, there's still a long way to go, I'd say, to on our journey of using Alluxio. And then I'll hand over to Beinan to talk about some great work on his end.
I just want to use your share screen. Hello? Can we go to the next page?
Volume is quite low.
Hello? Can you hear me?
Yeah, I can hear you, but like the volume is very low, at least for me. I don't know.
Now, is it okay?
Oh, it's not better now.
Okay, so yeah, let's go to the next page. Thank you.
So do you want me to?
Yeah, just next page. Next.
Okay.
Okay, thank you. Thank you, Chen. Yeah. Yeah, just as Chen mentioned, we are using the cache filter to improve the overall hit rate. And the next step, actually, we just want to put more tables into the filter. But the problem is, which table should we put? Should we just add it to the whitelist? Because we found for some of the table, it's super bad. It will quite lower down our hit rate. I will explain why. Because for Presto query, especially for the ad hoc query, just like what I draw in this diagram, it will scan multiple tables, and for each tables, they may contain hundreds or thousands of partitions, and for each partitions, they may have multiple files, maybe hundreds of files, and also in this file, there may be some cold data, maybe some hard data, and maybe some new data, maybe some stored data there. Especially for some large query, maybe it will touch the data maybe 3 years ago. For some cluster, maybe for this query, it's just a one-time data access. So for this kind of data, maybe there's no value for us to cache. So that's why we wanted to add a table of, we can see, partition level metrics to monitor which table or which partition is the most popular data, and it will be accessed again and again, and we should put it into our cache. Okay, next page. And in order to doing so, we changed a little bit on Presto side. We passed in the cache scope. The cache scope contains 4 terms: database, schema, table, and partitions. We will pass in this to the local cache. And the local cache will generate quite a few counters for each table or each partitions. Now we are just using the table level metrics. I will explain why. And now we have 2 choices. One is we can reuse the Alluxio's metric system. We can expose it to the JMX, to CSV, or maybe some other metric system. But meanwhile, we can also expose the metrics to an in-memory storage. Actually, it's just hash map-based storage. I think our customer, our users can use this implementation to expose the data to some logs. I think by this 2 approach, we can monitor the data access of each partition or tables. Okay, next page. Okay, yeah, here is just an example about a dashboard. I'm just use the premise use to monitoring the data. I just have one table called the TPCDS customer. We can see for some of the metrics keys, we have the table name in the middle. But for this one, we are just using the JMX. So I can see that for a table level, it might be okay, because now we just put 20 tables in our cache filter. And that means we are added something like maybe 100 or 200 matrix keys into a JMX. But if we want to monitor the partition level, it will be too many JMX keys there. So that means we cannot use the JMX. Maybe we need to use the, as I mentioned, the in-memory storage, and we need to implement something there to integrate that one with your monitoring system to have some insights about the partition level hit rate. Okay, let's just focus on the table level metrics. By using these three metrics, like something like the byte read from cache or byte read from external, we can calculate the hit rate of each table. We can adjust the parameter, something like the maximal partitions in the setting to see what's the best value for this table. And also for some of the tables, that might be just no value to cache. Maybe it's too huge, or maybe it's too small or something. So we can just skip it. Maybe we can kick it out from the cache filter. Okay, next page. Yeah, the other thing is also, like Chen mentioned, we are seeing some performance degradation when the cache doing a lot of the eviction. We are thinking about, just because we are not cache the keep updating data in an efficient way, because we will keep generating the new cache key for the new data. But actually, the data update is on the file level or partition level. So that means if a file or partition got updated, we can just kick out all the data stored for this file or partition just in one time. So we implement a file level metadata for our local cache. At the very beginning, we developed this feature just for to persistent this kind of data, just for if we restart the Presto server, we can still keep some metadata. But then we found this one might be also helpful for the data eviction, because now we have file level metadata. We know the last modified time of each file or partition. Okay, next page. Yeah, okay, I will talk a little bit about the future work on Alluxio side, because Chen already talked something about the work on Uber side. We will keep improving the cache efficiency by improving the cache filter, by improving the animation or the eviction logic. And also, we will do some optimize for the SATA or mechanic hard drives, because now we are more optimized for the NVMe SSDs. The read of the cache is more like a randomly pick some pages, but if we are using the mechanical hard drives, it's really difficult for the drive to seek to the page on the disk. So maybe we can use something like a RocksDB or some other LSM based database or storage to store our page. We can combine with the memory. We can improve the efficiency of the read. Also, we will adopt the shadow cache, because the metrics we just talked about is just for the data we already cached. It's already in the cache filter. For this kind of data, we already have some data or something kept in the memory. So we have some data about the hit rate, how many data read from the cache, how many pages we read from the outside. But what if the data is not in the cache? We have no idea, especially for the data already evicted from the cache. Everything is gone. So now we have a good implementation for we call it shadow cache. Just use something like a Bloom filter or Cuckoo filter to keep the everything, the meta for every partition or files in the memory, but just based on the implementation of this awesome algorithm, the memory usage is super small. We can use just very small memory to keep a large amount of metadata of the pages. And also based on this, we can do the partition level popularity estimates. I think based on this one, maybe we can implement some dynamic cache filter, not just based on the configs written by the humans. We can just use this shadow cache to implement something like based on the runtime data to calculate which partition should be more valuable to cache. Yeah, I think that's everything I want to share today. Thank you for joining the seminar. Now I think we can go to the Q&A section.
Cool. Thank you. Thank you, Chen, and thank you, Beinan. So let me see. I don't see question yet, so I'm gonna go ahead and ask my question. So I'll post it on the Slack channel again. So I think this question may be for Chen. So for the cache filtering, it is mentioned that we have manual and static configuration. So do you see that, given that the traffic pattern is measurable, do you think it can be automated and make dynamic in the future?
Yeah, absolutely. That's what the point about using shadow cache comes in here. So basically, we expect the shadow cache feature could help us, shed some light on how much value we can gain if we cache this specific table or this number of partitions. Then use this information, we can have, basically a simple service to, just add that table to the cache filter, or even remove a table from the cache filter. So yeah, I definitely see ways we can make this automatic. That'd be one for future work we are trying to work on.
Awesome. Cool, that's a question I have. And given we're running out of time, I'll let you guys go. And for everyone, if there's more questions, please ask in the Slack. Thank you. Thank you, Chen and Beinan.
Yep, thanks.
Jasmine?
Yep, thank you very much. All right. Thank you, Beinan and Chen. And again, you guys can find Beinan and Chen in our community Slack channel, along with all the Alluxio contributors. Please don't hesitate to post your questions there. Like Jingwen said, we will also have the recap pages up after today's talk as soon as possible after the conference. And I sent the links on the Slack and via emails for those registered audience. So if you have access to and so you can have access to the links and material of those presentations.